Mini 6. We are given a nice little situation where we have an object on an inclined plane which is held by a string, and the string is obviously parallel to the inclined plane. What's given to us? The mass is given to us. It is attached by a rope which is massless and unstretchable, so we don't care, to a vertical wall, and the system is at rest. Initially, calculate the magnitude of the normal force acting on the object as well as the tension along the rope. And we're given alpha. So, based on the keyword, which Newton's law are we going to use? Which keyword allows us to figure out which of the two or the three laws we're going to use? I'm doing part 1. Which law can we use and why? Excellent, Jonathan. Thank you. Keyword at rest. Therefore, we know the acceleration is 0. Therefore, we are going to use Newton's first law. All right, good. That makes life easy. So, second, let's identify our system. We only have one system here. We're looking for the normal force acting on the object, the block. So let's pick that as our system. Now we know that the block is our system. Let's identify all the external force acting on it. First one on the list, the weight, always down. And in this case, we know it entirely because we know the mass. Second one, normal force. Obviously, the block is on the inclined plane. The normal force must be perpendicular to that inclined plane and acting on our system. Therefore, it must be going up and left. Third, is there any pushing or pulling? Well, obviously, there is a rope that holds the block where it is, so it's putting it up. Therefore, let's put a force there and let's call it T, which is a good comma because that's what they're asking us, the tension along the rope. Perfect. There is no mu s and mu k given to us, therefore no friction, therefore that's it. All right, now that we have identified all the external forces, which are contact forces except for the weight on our system, let's do and complete our free body diagram. So let's represent this by a zero-dimensional point and draw all the forces from that point. W, T, and N. Second stage, let's pick a coordinate system. How would you like to pick your coordinate system? Can you give me a candidate for your positive X and a candidate for your positive Y? All right, team suggests X along T and N along Y, which is confirmed by Honoka. X along T and N along Y. Excellent choice. Why is this an excellent choice? Because we know by the property of the normal force and the diagram given to us that T and N are perpendicular to one another. So let's pick our two axes along this direction, because now the component notation of T is trivial and the component notation of N is trivial. We only have to work out the W. If you had chosen this coordinate system, you can do it too. You just have more work, because now you have to identify the angle for T and the angle for N. Therefore, as you apply chapter 2, you're going to have to think about the sine, the cosine for both of those vectors. While the choice given to us or the solution given to us by Tim and Onoka makes our life much easier, we only have to worry about W. So it saves time. So choosing the adequate coordinate system will allow you to simplify your algebra dramatically. And I know that most of you love algebra, so please use those tricks to minimize it. And I was being sarcastic. But I would strongly suggest that as you practice those problems, pick X and Y like we did, and then redo the same problem by picking the X and Y horizontal and vertical. That will allow you to practice your vector. Go back to chapter 2 and practice, practice, get better at it, get faster at it. Good. So now we need to figure out the angle between omega and between X or Y. How are we going to do this? Obviously, alpha is involved with W. I'm sorry, not omega, W. But where is alpha? Is alpha between W and negative Y, or is alpha between W and negative X? What I would suggest to do is draw where alpha is, somewhere on your diagram. Alpha is this angle. So the question is alpha between W and minus X, or is alpha between W and minus Y? And alpha is not 45. If you draw your right angle triangle, you should be able to see very, very easily that if this is alpha, this cannot be alpha. Do we all agree? By basic geometry, if alpha is not 45. So just by this argument, you know that alpha has to be between W and Y. Does that make sense? So that's the first method. This one, works often, but doesn't work all the time. The method that will work all the time, that will allow you to figure out the direction of any one of those stupid vectors with either your X or your Y, is as follows. It's a two-step method. Make sure you take good notes, because if you get that angle wrong, this is where I'm going to stop giving you points. If your free body diagram is incorrect, all your equations are incorrect, all your answers are incorrect. So make sure that you spend a lot of time on those free body diagrams. You make them big, you make them precise, and you make them correct. And the direction is sometimes where people have trouble. So let's look at the method. Two-step method. First, we're interested in W, so focus on W, the black dude, going down. Then identify the two lines that create your angle. In this case, the purple ones. Those are the two lines that create and define alpha. First question, first step, follow the direction of your force that you're interested in and ask yourself, is the direction of that force perpendicular to one or the other of the line creating that angle alpha? In this case, obviously, the direction of the force is perpendicular to the horizontal line that creates alpha. This one. Hence, forget about it. Focus on the other one that creates alpha. And ask yourself the second question. Is this other line perpendicular to your X or your Y? If it's perpendicular to your X, then your angle is between your force and X. If it's perpendicular to your Y, then this angle is between your force and Y. Hence, alpha is here. Okay? Foolproof method never, ever fails. First, identify the two lines that creates your angle. Then look at the direction of your force and ask yourself, is the direction of my force perpendicular to line 1 or line 2? If it's perpendicular to line 1, forget about it and focus on line 2. Then ask yourself the second question, is my line 2 perpendicular to my X? If the answer is yes, then the angle is between your force and the X-axis. If the remaining line is perpendicular to your Y-axis, then this angle is between your force and the Y-axis. That's it. Very easy, very fast, two-step process. So make sure you write them down, and every time you do a Newton's problem in chapter 5 and chapter 6, you use it. Perfect. So now my free body diagram is complete, and I can erase all that stuff. Now I'm ready to just write the equations. Easy. Newton's first law is going to give us two equations. Sum of forces in the x, sum of forces in the y. Let's start with t. T is already along x, therefore tx is t, and ty is 0. N. N is along the n, therefore obviously nx is 0, and y is positive n. And then for the w, obviously the right angle triangle is the one between w and y, therefore the x component is negative mg sine, and if one is sine, the other one is cosine. You just have to check for the direction, negative as well. So again, this is chapter 2. So if it takes you more than 30 seconds to go from your free body diagram to your equations, you should realize that you need to go back to chapter 2 and repractice, 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 repractice. So make some cases up. Pick a bunch of forces, pick different coordinate system, and practice, practice, practice. And if you want me to check, bring them on Wednesday, or stop by my office, or take a picture, send it to me via email, and I grade them all until you master that step. This is the step where 90% of the people make mistakes. And it's not just in 170. They still make mistakes in 270, which is infuriating. And then they still make mistake is 271. But usually if they make that many mistakes in 270, they just don't survive. They never pass, and they drop out of engineering with respect to ME and CE. So please, this is the core. If you want to be a C and ME, you need to master this. It needs to become second nature. Otherwise, you will not survive 270. You will not survive 271. That's the bread and butter of Newton's analysis for ME and CE. So please practice. It may be a little bit weird at first, but as you practice over and over and over, it's going to become easier and easier. You can become way faster and way faster and way faster. And at some point, poof, you'll do it in your head. When you reach that stage, you're good to go. Okay? So, now the rest is trivial. What the heck are we looking for? Calculate the magnitude of the force and the tension. So, let's identify the number of unknown. Magnitude of the force along the rope, that's T, and the normal force, N. Everything is known. Therefore, we have two equations, two unknown. Perfect. Now we can solve. In this case, it's trivial. The tension is just going to be mg sine alpha, and the normal force is mg cosine alpha. The n that I add at the end are the units. Don't forget the units. As you've noticed, all the magnitude that we've calculated so far and that you will get for the rest of the semester have to be positive. As you solve for t and n, if you ever end up with a negative value, you know something is wrong, so don't leave it. If you leave a negative value, that suggests to me that you have no idea what you're doing. Remember, the magnitude of a force represents the length of an arrow describing that force. The length, magnitude, all those have to be positive. The negative sign shows up because of the directions, okay? Which were indicated right here, if any. So the final answer, as you solve for it, have to be positive. If you have a negative value, 3 sources. But 2 sources. Either, I'm sorry, 3. You messed up with the algebra, or you messed up writing your equation from your free body diagram, or you messed up your free body diagram. If that's the latter, the fix is easy. That means you picked the wrong direction for that particular force. So just flip it, and you solve the problem. So again, very, very easy. But never, never neglect a negative sign at the end, because that's impossible. And this will become fundamental if you decide to take C270, because there are going to be cases where you're going to have to apply not one free body diagram to solve the problem, but 5. And they're all going to depend on each other. So if you neglected a negative sign on the first one, the reader doesn't have to read the 4th other free body diagram. Everything is going to be wrong. And therefore, the amount of points allocated is not going to be that much. So never forget to identify any possible negative sign. Don't neglect them. They always mean something. All right, next stage. Any questions? Jump in anytime. Then we decide to cut the rope. So obviously we're at rest, we cut the rope, and that will cause the block to just slide down the inclined plane, obviously. So how are we going to figure that out? They want to figure out the velocity of the object after it has dropped a vertical height of 2 meters. So we started from rest, that still holds. And after it has dropped by a particular distance, so x or y, they want the velocity. Rest confirms that v0 is 0. After giving a condition about position, they want velocity. So obviously the equation that we need is going to be this one. If we pick x along the inclined plane, which means we have to figure out the acceleration. There will be an acceleration as you cut the rope. However, the interesting thing here is the acceleration that will be created along the inclined plane is not due to one force. It's only due to the component of one of the forces. So you don't have to invent a force and create one such that there is one along the direction of the acceleration. This case reflects the fact that it's actually one of the components of the weight that will do the job. So we don't need to invent another force. So if we cut the rope, then really we're back to this situation. That's it. So the only change between part 1 and part 2 is we only have 2 forces, W and N. We know the acceleration is going to be down the inclined plane. That's physical constraint, common. But we don't need to insert a new force along the inclined plane down because it's not on our list. There's nothing putting, nothing pushing. There is no friction. So we don't have to invent another force. This should do it. And as you look at this, you will see naturally from chapter 2 that really the one that will create acceleration is this little bugger for W. Okay? So since we want the acceleration along the inclined plane, let's pick a coordinate system along that plane. Again, we need to complete it. Therefore, we need to figure out the direction between W and the Y axis. We've already done this. That doesn't change. It's alpha. So really, the only difference is T is 0 in this case, because obviously we cut the rope. So let's write down both equations again. Even though one is going to be useless, one is going to give us n minus mg cosine alpha is equal to 0 because there is no acceleration in my chosen y, because I chose my positive x to be along the acceleration. Hence, this one I know is ma, positive. And in this direction, the only force that's present is positive mg sine alpha. Just from chapter 2. And that's this guy. So it was really one of the components of the weight that did create that acceleration. Now we can solve for A. And A is g sine alpha, which you most likely will see this in lab. Verify that. Very easy results. Again, remember, G is positive, positive 9.8. We chose a positive x to go down the inclined plane. This is where the block is going. Therefore, it got to be positive. If we end up with a negative value, something is wrong. And sure enough, I repeated many times, G is positive 9.81, always, always, always. The negative sign shows up because of your coordinate system. Good. So now we can squeeze this into our equation. If we start from rest, V0 is 0. V obviously is going to go down the inclined plane after a particular distance. Therefore, V will be positive square root of 2ax. And we can substitute the acceleration in there. But then the last step is to be careful. Do we know everything? Well, we know G, that's 9.8. We know alpha, that's, I don't know what that is, 35. But what is X? Well, X must be consistent with the current system. This is X. So the X that shows up in my equation is the distance along the inclined plane. But that's not what's given to us. They're only giving us the vertical drop, the vertical height. So if you go down the inclined plane with an angle of 35, they're telling us that the block was here when we cut the rope. They want to figure out the velocity along the inclined plane as it goes down if he has dropped by this distance. That's what they give us. That's what is 2. That means we have to use that information to obtain this distance. That's my X, because that's where I put my positive X axis. So, can anybody relate this X with 2 and alpha? And give me the functional form that relates those 3 buggers? Yeah. Thank you, Anoka. Excellent. Obviously, by geometry. 2, wait, how does that go then? How do we use a sign? I got a brain fart. Help. What is the exact relationship between x2, alpha, and sine? Just to make sure we all remember our geometry. Pythagorean theorem, right? Same thing as triple 2. X times sine alpha is equal to 2. Excellent. Therefore, X is equal to 2 divided by sine alpha. Or sine alpha is equal to 2 over X. They're all the same. We're interested in X, so let's solve for X. Therefore, I'm going to squeeze that guy right here. And V is 2G sine alpha. X is 2 sine alpha. Square root. Therefore, 2G. Hey, nice answer. Very easy. Okay? We don't even need a calculator. Questions on this?